Okay, so I think we can start. So
Okay.
welcome to this last seminar of today by Giacomo Ascione on non-local Schrödinger operators with eigenvalues at the spectral edge. And I see that it's based on joint work with JozsefL&ouml, which is one of our co-organizers. Thank you.
So first of all, let me thank all the organizers for letting me talk about this quite in my opinion, interesting. So I think I would like to convince you that it's quite interesting work. So, and let me just go straight to the point. And so we consider a measurable function that goes to 0 as x goes to infinity. And let us call it a decaying potential. And we know with the same ladder the multiplication operator that associates to a function in L2 the multiplication v of x times this function in L2, and then we use this to define a Schrödinger operator. That's quite a classical thing to see in general because it's actually the main operator in quantum mechanics, as it is the description of a particle wave in quantum mechanics is completely determined by this operator here. And the spectrum of such operator actually, as usual, can be decomposed in discrete spectrum. That is to say, the set of all the eigenvalues of finite multiplicity that are isolated points, and the essential spectrum, that is everything else. However, I'm saying that in the discrete spectrum, the lambda that belongs to the discrete spectrum must be at the same time an eigenvalue and an isolated point. So there could still be some eigenvalues in the essential spectrum. And such kind of eigenvalues are called the embedded eigenvalues. So historically, embedded eigenvalues have been found in different situations. For instance, the first case was studied by Neumann and Wigner in 1929, and they proposed a potential that admit a decaying potential on a tree that admit 1 as an eigenvalue. It is a positive number, so it belongs to the essential spectrum of the Hamilton operator. And in 1959, Kato showed that, well, you can only slightly improve this example because if the decay of the potential is too fast, then we cannot have any positive eigenvalue. However, we can still make things quite awful, let me say like this, by creating some potentials that admit a dense set of positive eigenvalues in the essential spectrum. And since then, there has been a rapidly growing literature in what we can call Neumann-Wigner potentials. That's these potentials that meet positive eigenvalues. However, we are talking about positive eigenvalues. So we are excluding this little number here. It's quite infamous in a certain sense. That is the 0. So for the 0 eigenvalues, things are quite more difficult. First of all, let me just cite a result by Agmon that says that there is a condition, a sort of compatibility condition between the positive part of the potential and the eigenfunction, so that we can actually have a 0 energy eigenfunction. However, this cannot happen if the positive part of the potential is sufficiently summable, belongs to L at 3/2 in the case over 3. If we consider P to be greater than 3/2, then we have a condition on the actual decay of the positive part of the potential. And this constant is sharp in the sense that if as x tends to infinity, the positive part is greater than 3/4 modulus of x squared, then you can actually construct a potential that emits a 0 eigenvalue, that emits 0 as eigenvalue, so a 0 eigenfunction. There are also other conditions that link the sign of the potential and the sign of the green function with the existence or non-existence of zero energy eigenfunctions, and the sign of the potential itself, as I said before. For instance, there's this result by Yafev that says that if I consider a positive decaying potential that decays like this, then I can actually have a zero eigenvalue. But if I consider it to be negative with the same exact decay, no zero eigenvalues at all. So for the zero eigenvalue, we have a much more complicated scenario in which, well, things can be really, really critical. As for instance, the decay 1 over x squared becomes critical if I can, depending on a constant that is, for instance, in this case, it's the constant 3/4 that creates this division between the case in which 0 is an eigenvalue and 0 is not an eigenvalue. So as I said, if I consider a decaying potential of this form, then if gamma is greater than 2, we do not have 0 as eigenvalue, and if gamma is less than 2, we could have 0 as eigenvalue. But when gamma is equal to 2, it depends on c, and when c is greater than 3/4, we can have 0 as eigenvalue, but we lose this property as c is less than 3/4. So what we are actually interested in is what happens when I substitute the minus Laplacian in the Hamilton operator with a suitable non-local operator. That is to say, phi of minus Laplacian, where phi is a suitable complete Bernstein function. And just to give 2 examples, we can consider phi to be lambda at alpha half, for alpha between 0 and 2, that leads to the fractional Laplacian that, well, we actually talked a lot about this. And we could consider phi to be something like this to obtain something that we can call the relativistic fractional Laplacian. So up to now, I said, what are we interested in? But I didn't say, why should we be interested in such a thing? Why this zero eigenvalue is quite interesting. Why should we move to a non-local object? And actually, let me just focus on this, at least to give us some sort of justification that I hope will be convincing. So as I said before, the Schrödinger operator actually describes the particle wave dynamics in quantum mechanics. So actually what I'm saying is that the solution to the Schrödinger equation describes the so-called probability wave of the particle. So how does one just obtains the Schrödinger equation from just an heuristic point of view, because actually the Schrödinger equation is an axiom of quantum mechanics. So just from a completely heuristic point of view, how do we actually obtain this equation? Well, we start from the energy momentum relation in the classical mechanics. Here, p squared over 2m is just the kinetic energy, and here we have the potential. And then we map the energy into the time derivative, the momentum into this operator here, that is just h bar over I, where h bar is the corrected Planck constant times the gradient, and then v becomes its multiplicative operator that we call with the same name. So here we have something that seems to be a tautology, but its v function becomes v multiplicative operator, and then we obtain that this relation here becomes this relation here applied on a probability wave. That is actually a time-dependent classical Schrödinger equation. And when we try to solve an equation like hc equal to some constant times c, we are actually trying to find bound states that are the physically stable states of the system. And why the main motivation for the fact that these are physically stable states is just the fact that when we solve this equation, then we can just reconstruct a solution of the time-dependent classical Schrödinger equation by using a time shift. here, but this is just a phase shift, actually. Sorry, I said time shift, I wanted to say phase shift. So actually, time dependence is just a phase shift in the system, and this represents actually an equilibrium state of the system. And there are a few examples that are solvable, but let me just focus on this. That is quite the most important one, that is the hydrogen atom in the vacuum. So we consider just the Coulombic potential generated by the nucleus of the hydrogen atom. And then we can solve the equation by obtaining that the energy of the bound states are represented by this formula here, and the bound states themselves are actually obtained by means of Laguerre polynomials and spherical harmonics, and these numbers n, m, n, and l are the quantum numbers. And actually, this formula is not just a mere theoretical result, because it can be observed from some physical phenomena, such as, for instance, if we observe the wavelength of the emitted photons when the electron of the unique electron of the hydrogen atom decays from an energy state to another, and for instance, we obtain something like that, like this, that is what is called the Lyman series. Well, these energies depends on n here and go to 0 as n tends to infinity, but 0 is not an eigenvalue of the system. There are also other effects that are linked to the fact that 0 is not an eigenvalue of the system, but is still something of the system. So some effects like these are, for instance, the FDE2 effect. That is to say, what happens when three particles, for instance, we can consider three bosons that have some pairwise interaction, but each of these pairwise interaction does not have any bound state with negative energy. But the three-body system still exhibits infinite bound states, and these states are of this form, where lambda is a universal constant. And this has actually been observed in some cold atomic gases. For instance, it has been first imagined in rubidium type Bose-Einstein condensates, and then it has been observed in caesius Bose-Einstein condensates by the Green group in 2006. And actually, this phenomenon is linked to the fact that 0 is not an eigenvalue, but it's a resonance. That is to say, the equation still admits an eigenfunction in a certain sense, but this eigenfunction is not a real eigenfunction in the sense that it's an L2 eigenfunction, but it's LP for some other P. And there are also other phenomena that are quite similar to this FDE2 effect. For instance, the behavior of the neutron halo nuclei that are called Borromean nuclei, and as for instance, the lithium-11 that is composed of a nucleus of, well, we have 9 neutrons in the nucleus, and then these 2 neutrons that actually move free in the halo of the nucleus. And if I remove just one of these 2 neutrons, then the atom actually decays, just ejecting the other one. So what we have is that the three-body system is stable, but not each one of the two-body systems. So how do we move? So this is actually the motivation for which one is interested in proving that 0 is not an eigenvalue, or 0 is an eigenvalue, or 0 is a resonance, because we actually have some quite bizarre behaviors, for instance, in three-body systems. But then why do we move into the non-local setting? Well, the Schrödinger equation is actually Galileo invariant, but it's not Lorentz invariant. So it's not compatible with the special relativity. And we have to reconsider it from a different point of view. So in special relativity, we have this momentum energy relation. And if we try to use the same substitution as before, we obtain this equation here. And if we consider also the rest energy, we obtain something like this. There is 1 of the operators we have introduced before, as we will see. However, this is not really a relativistic equation. This is due to the fact that actually there is no symmetry between the behavior in time and the behavior in space. Let me just stress out that as t tends to infinity, we actually obtain the classical Schrödinger equation in the strong resolvent sense. But what happens is that this is not really a relativistic equation, but it's a decent approximation. It's easier to study than the direct equation, and it's actually a parabolic equation in place of the wave of the Klein-Gordon wave equation, that is an hyperbolic equation. And in the case we consider natural units, so we consider c and h bar to be 1, then we obtain this operator here that we've seen before. So that's why one is interested in moving into the local equation, because the local equations are quite a good approximation of what happens in special relativity in this setting. And actually, we can study the hydrogen atom in this model here, and we obtain again that En behaves like minus a constant over. However, this time we have an n decay in place of n squared, and still it goes to 0, but we don't have 0 as eigenvalue. Moreover, I talked about the Efimov effect, but the Efimov effect happens in a small scale, and possibly it could happen at high velocity. So actually, it does not happen in a classical setting, but more in a relativistic one, because we are at high velocity. So once we establish that we are interested in this in this zero energy eigenfunction in this non-local setting, well, let me just stress what is known about this setting here. And for positive eigenvalue, so moving from the zero energy case to the positive setting, we have some result by Lorenzi and Sasaki for the construction of Neumann-Wigner potentials for the relativistic operator. And then we have also that if the L-infinity norm of the potential is too small, then we cannot have any embedded eigenvalue. However, for the zero eigenvalue, things are again quite more difficult. We can still construct potential that emits zero energy eigenfunctions when we consider the massless case. So we are just considering the fractional Laplacian. And in a work by Caleta and Lorenzi, we have some information about the decay of the zero energy eigenfunction. And then there is this construction by, okay, I don't know if I can pronounce it quite in the right way, but let me just say, yeah, I think. Okay, I'm not very good with pronunciations in these cases. I'm actually not very good at pronunciation at all, but so yeah, Lorenzi, in a work that is still in progress, they constructed a family of potentials that admit, let me just stress that it's an explicit family of potentials for the fractional Laplacian, for the fractional Schrödinger equation, that admits zero energy eigenfunction. And they just work well in a full scale of asymptotic behavior. And I'm going to details right now. So just as I said before, that in the work by Caleta and Lorenzi, this one, we know that the decay of the eigenfunction, of the zero energy eigenfunction, depends on the decay of the potential. But then if we want to use this as an eigenfunction, we're going to construct the potential backward. That's what actually one obtains using the potentials by the work in progress by Jan and Lorenzi. Then we have that this potential here behaves like the modulus of x at minus alpha when k is between 0 and the half, except for this value here. For this value here, there are some cancellation effects that actually improve the decay. At d half, we have the appearing of a logarithmic term in the behavior, and then right after, we have a completely different scaling. So here we have minus alpha, And here we have 2 kappa minus d minus alpha. And the transition between these two settings is given by this logarithmic scale. Let me just stress that this function here belongs to L2 if and only if kappa is greater than the fourth. So in this case, when kappa is less than the fourth, we actually have that 0 is not an eigenvalue, but it's a resonance. It is still a resonance. Let me also stress that they actually construct a more large family of potentials in the eigenfunctions by considering some harmonic polynomials in place of this constant here, 1. I just consider 1 to exhibit this range of asymptotic behavior. Moreover, we also have that the decay of phi strictly depends on the sign of the potential. Vice versa, depending on the decay of phi, this potential here has different signs at infinity. So we have some sort of twofold behavior. On one hand, if we know the sign of v and the decay of v, then we know something about the eigenfunction. Vice versa, if we know something about the eigenfunction, it seems that we can know something about the potential that generated it. So what we want to do is to mirror what we have here. So the idea is that we want to prescribe the behavior of the eigenfunction and say, well, if we suppose that we have an eigenfunction that behaves like this, what happens to the potential? Does there exist a potential that actually admits such an eigenfunction? Or should I search for some particular potentials that admit such an eigenfunctions? And that's actually the work I want to talk about. So let me just now go into details. We consider for this work a complete Bessel function of this form. And actually we can consider also the drifted case, but I want to avoid the drifted case by now. I just want to consider just the non-drifted case. And on a certain domain that I won't go into details right now, we can define this operator like this. And this operator here, this exponential here is just the Hit semigroup. And then once we represent the Hit semigroup like this, we could recognize some integral representation in here of this operator, some sort of Marshall-like integral representation, actually a Ritz-like integral representation, to be honest, because if we consider phi to be the just the stable case, is to say lambda at alpha half, we obtain the Ritz potential. So let me just go into details that from this point of view on the fact that I say that here we should have some jump kernel. So the operator I was talking about before is the generator of a pure jump RD-valid isotropic Levy process. And such isotropic Levy process is actually a subordinated Brownian motion whose Levy measure is given by such a formula where J is the integral of a Gaussian against, sorry here, okay, yeah, it's R, against the density of the Levy measure of the Bernstein function P. And so by using the jump kernel, we can actually represent this in this way. And this is quite well known if we consider this Bernstein function here, that is nothing else than the fractional Laplacian. So this function J becomes actually the its potential. Well, we can actually play a bit with this integral representation because J, so for instance, I can change variables and put x minus y equals to h. So here we have something that resembles, in a certain sense, first order difference. And then the principal value I can recognize it as to be the limit as the radius of a certain ball goes to 0 of the integral taken on the whole space except this ball. But then J, by definition, is quite, you know, rotationally symmetric. So we can just play a bit with the with this integral and then rewrite it. Sorry, I just have to move a bit. Okay. And then rewrite it as this form here, where we do not consider actually a first order difference, but a second order difference. Why should we consider a second order difference in place of the first order? Is just because actually we can recognize, at least for instance, for alpha big enough, something that behaves more like a second derivative than a first one. Second order differences are actually discrete approximations of the second derivative in a certain sense, except we should divide by h squared here. So we can actually characterize functions for which this equality holds pointwise by saying something about this quantity here. So let us introduce some notation. We say that a certain modulus of continuity is radially integrable with respect to the measure mu if B composed with the modulus is L1 log. And then we introduce something that we can call as some sort of Zygmunt-Elder type condition with respect to a different beta. Beta here will be always a modulus of continuity. Actually, we won't consider again beta, but then at a certain point we just say, well, beta will be h squared. Stop. And we consider only the quadratic case. But actually, all the things I'm saying here hold for any beta that belongs to this class for a fixed Levy measure mu. So what I call a Zygmunt-Elder type condition is something like I can control the second order difference via a constant. Actually, I can consider a function in place of a constant, but for what I need here right now, I just need a constant here, times this modulus of continuity applied on the modulus of h when x is big enough, when h is small enough, and small enough, and this small enough depends on the point x I'm working with. So I'm just considering the most general case possible. But then I can just prescribe some information about M and R. For instance, if I consider R to be linear, I just denote this space like this, and this is quite an important thing in what I want to say. And then I can consider actually R to be constant and then to be 0, so that I obtain something that quite resembles Zygmunt-Elder spaces. Actually, this is a Zygmunt-Elder space for some choice of beta. And let me just stress that by definition of Levy measure, such beta R squared precisely always belongs to this space here. So if I consider, for instance, beta R to be R at alpha with alpha that belongs to 0, 2, then if we are between 0 and 1, we are talking about just Elder continuous function, nothing different. But if we consider alpha to be 1, then we don't have Lipschitz continuous function. We have something that is bigger, slightly bigger, not C1, but slightly bigger. And then if we go further, then we consider something that is smaller than the set of Lipschitz function, because actually these functions here are continuous and Lipschitz. So sorry, just okay. So now we write just these spaces here without writing down beta. If we say that beta R is equal to R squared, and then since we represented the operator as a second order difference times the jump kernel, and the jump kernel is actually the density of a Levy measure, then we can consider beta to be some modulus of continuity that belongs to the radially symmetric summable function with respect to that Levy measure exactly. And then we have that if phi belongs to this space here, then this is pointwise well-defined for any x outside a ball. But if phi belongs to this space here, then it is well-defined for any x. So something that we are interested in is actually this function here that is just the supremum of the second order difference over h squared. However, in balls that are becoming bigger and bigger and bigger and bigger and bigger. But these balls are becoming bigger, but at the same time, they are running away from the origin. So what we obtain is that the bigger is the ball, the far away is from the origin. And well, we have this sort of so C here is between 0 and 1. That's why we are far away from the origin. And the behavior of such a function will play a major role. And well, we are interested in these 4 kind of behaviors, but I will go into details in 10 minutes. Let me just focus on this behavior here that I call phi. So these behaviors here we can just give them some name. This is a power-like behavior, a sub-exponential behavior, the actual exponential behavior, and then a super exponential behavior if we consider gamma to be greater than 1. But for the power-like behavior, this is quite a common behavior because we can just prescribe phi to be something like a radial function that just is C2, decreases, but then is convex at infinity, actually, but with second derivative is decreasing, and that behaves like a power. Once I ask for this to behave like a power and these other properties to hold, then at the same time I obtain that the function LC phi, that sort of supremum of incremental ratio behaves like the same power minus 2. So something like this, actually. And we are actually interested in the asymptotic behavior also for the measure mu. We distinguish between 2 cases. That is the power-like case. Actually, it's the regularly varying case because here I'm considering a slowly varying function. And the exponential-like case, well, this means that we are actually investigating the case of regularly varying function at infinity, regularly varying Bernstein function at infinity. But this case here is instead typical of the relativistic case. So to treat the relativistic case, we have to consider a completely different asymptotic behavior. This creates a whole difference in the behavior of the potential. And depending on phi and the phi, we obtain 2 different asymptotic behaviors of the jump kernel J. That is a power-like behavior that's quite typical of the fractional Laplacian, and this behavior here that is quite typical of Bessel potentials. And Bessel potentials are induced, for instance, by the relativistic setting, by the relativistic Laplacian. So we will use 2 auxiliary functions that are a sort of tail of the Levy measure and this integral here. And in the power-like case, we also used the LP norm of the function J. Let me just stress that actually this is not interesting in the iffy phase and in the iffy case and the exponential case, and this will be quite clear what follows. And so let me see what kind of equation we are studying. We're studying this equation here. So this the eigenvalue equation in the 0k. In the case we have a positive eigenfunction or a positive resonance that is bounded, nothing else, and such that the equation holds pointwise. And if this equation holds pointwise, we can recognize V to be something like this. So we can actually write down V as 1 over twice the eigenfunction times the integral of the second order difference times the jump kernel. So it is clear that the interplay between this integral here and this denominator here will characterize the asymptotic behavior of the potential V. So let me just jump this section here, just to say, I want to go that deep into the details of, not so much details, sorry, deep into something that is quite interesting. Let me just stress that we actually start with this bound, and this actually proves local boundedness of the potential. And we can use something like that to prove also continuity. And the way we prove continuity is just to write down this V as via first order differences outside the ball and second order differences in the local part, so that is to say inside the ball. And this can be done because actually the representation that I gave before in terms of the second order difference actually can be split into parts. And then one can say, well, I want to use the first order representation outside the ball, and then inside the same ball, I can use the second order representation. And then in this way, I can avoid passing to the limit in the principal value representation. So we have some symmetry results, but I want to jump straight into this result here. That is to say, if I consider phi to be in such a space, and I consider the same decomposition as before of the domain, then the local part, the part near the point I'm studying, gives a component that whose behavior is dictated by this second order difference term, this function big J, capital J, and the denominator phi, that is the actual eigenfunction. And then the global part, in a certain sense, is to say what happens outside the ball, is dictated by these two terms. One that comes actually from the just Elder and Elder-like, actually the actual Elder inequality, and then the Levy measure outside the ball we are considering. And if we have that all this part goes to 0, actually the last term goes to 0 without us asking for it, then we get that the potential is decaying. Furthermore, if V belongs to this space, then the potential is decaying, bounded, and continuous. However, how fast it decays depends on who between these two terms win in a sort of fight for who decays slower or faster, depending on the situation. For instance, if I consider the power-like case, the decay of the potential is completely dictated by an interplay between L, alpha, and K. When K is less than the half, then we have this potential here, this decay here, sorry. When K is equal to the half, we have again the logarithmic transition we had before, and then we go back to the behavior 2K minus D minus alpha. We just lose track of the case D minus alpha alt. That is quite a peculiar case of that potential that actually comes into play, because there are some cancellations that here, since we are considered just a bound, we just do not see some cancellation effect. And these actually are the actual decays of the potential we had in the example by and Rinczi. Except in that case, L was just 1. So how do we get this decay? Why do we have this decay actually? Well, this time, instead of considering a domain decomposition in 2 parts, we have to consider 3 parts. One, that is the local behavior near the point we are studying. Another one that is dictated by some sort of global behavior, but not too global in a certain sense, that is the blue region. And then the green region that is outside these 2 bounded regions. So, and we use second order differences to model what happens in the red region, while in the green and blue regions, we use the first order differences. In the red region, we have again that this is the leading behavior. And well, we said before, this is due to the actual fact that we are using second order differences here. We have this that is like a sort of Lipschitz type constant depending on the ball that is of radius c modulus of x. So the radius of this ball depends on the point we are working with. Then we have this capital J function over the actual eigenfunction. Then in both these regions, we have this part that is dictated by the Levy measure. However, in the green region, we have the Hilder type part, while in the blue region, we can control it by using the fact that phi belongs to L1 inside this region, and then we have J. Why do we do this? Because actually, what happens in the blue region when we use the L1 changes the whole behavior of the whole asymptotic behavior, because everything that happens in the red region, or the behavior of the tail of the Levy measure, or for instance, the Hilder part, is something like modulus x at minus alpha L of 1 over x squared. So if the blue region behaves like these three parts, then we win. We actually have the exact behavior. It's modulus of x at minus alpha L of 1 over x squared, and we are happy. Well, that's not the case. In the blue region, we could have different asymptotic behaviors depending on kappa. That's the real problem. So while we change kappa, we obtain in this blue region different asymptotic behavior, while in the whole space, things are always the same. And the winning part, in a certain sense, the slowest part, the part that actually dictates the behavior, is this blue part here. Let me stress that the blue part is far from the x point. So we are saying that the whole asymptotic behavior of the potential is actually a global matter. It's something that depends on what happens far away from the point we are actually working with. However, if we go into the exponential case, you obtain something that is, I just wanted to say something that is quite magical in a certain sense. So let me just recall that for the standard case, we had that 3/4 modulus of x squared discriminant between the existence or the non-existence of the zero energy eigenvalue. So if we have a zero energy eigenvalue, something that must decay at least as x at minus 2. So in the exponential case, we got the same thing, exactly the same thing, independently of k, which is something that quite resembles the fact that, well, maybe this case is more similar to the classical case than what we expect. The question is, can we improve the decay? So is it just a matter of we just use some not sharp calculations and then you obtain 1 over modulus of x squared because we were lazy and we didn't think about something better? Well, actually, there are some hypotheses that guarantee that the potential decays exactly like x at minus 2. And these are some kind of excess conditions on the eigenfunction that are actually verified, for instance, by some particular radial functions. The function I said before actually verifies this condition here. And why is this happening? Why we lose track of the decay of the eigenfunction when we move to the potential? Well, let me just give the same decomposition as before. And what we have here is that we can actually, it is not important to consider just the difference between green and blue region, because if we go back to the same, what happens is quite peculiar, is that if we go back with the same exact bounds, then we get the same exact asymptotic I'm showing here. So let me just give the easiest case, that is to say we control it via Hilder inequality with exponent infinity. And then what happens is that here we should have something like this. That is quite, well, not so good asymptotic behavior, because we have d minus alpha minus 4 plus 4k over 2. It's quite awful to read. Here we have, however, here we have some exponential behavior. So we have that the potential should decay really, really fast, but then the local part kills it all. And why does the local part kills it all? Well, it's because this capital J is bounded in this case. So it does not play any role in the asymptotic behavior. So just the importance of this difference is that the red region, as I said before, is just a local effect in the decay of the potential, while the blue region, the green region are long-range effect. And what is happening is that in the power type decay for the Western function, global effects, long-range effects are leading, while in the exponential case, short-range effects are leading. In the fight between locality and globality, in the exponential case, locality plays a major role. It's not that locality is the only thing, but locality plays a major role. So, however, something that one could ask is, can we just obtain some potentials that behave like different power scale in the exponential case? Well, this could be done if we ask for the function phi to be, again, exponential. Let me just stress that all the hypotheses we are giving on the decay of the function LC phi can be actually verified if we consider phi to be actually equal to this function here in the one-dimensional setting. So just to see that these are not quite, how can I say, these are not just, we're choosing just the right decay because it's the thing we are interested in. It's just because we are considering, maybe we could consider the one-dimensional case, and then here we can consider equalities. If we consider equality here, we get the equality here. And again, what happens here is that depending on the decay here in the exponent, we get different power-like decay of the potential. And again, the behavior is due to only to short-range effects. Long-range effects are still exponentials, and since they are exponential, they decay quite faster than the power we have in the local case. And again, the same hypothesis before give us that this is an exact decay in some cases. If we try to do the same in the power type decay, we get this condition here. That's awful, because in this case, the potential, the Schrödinger operator admits poorly discrete spectrum. So what we obtain is that if a potential admits a zero-energy eigenfunction, such a zero-energy eigenfunction cannot decay like this. Vice versa, we cannot prescribe any potential that in the power decay case admits exponentially decaying eigenfunction, and this is the same in the exponential case. We consider the super exponential decay of the eigenfunction. Just to say the last thing, and then stop, the exponential case. what happens if we consider exponential decay of the level measure and exponential decay of the eigenfunction, then again, we have some critical constant that separates the fact that we could have a zero-energy eigenfunction and we could not have a zero-energy eigenfunction. Because if eta, this decay here, is greater than the square root of eta, where eta is, so if eta phi is greater than the square root of eta here, then we have again a confining potential. And for confining potential, we cannot say anything. But in the other case, if we have that eta phi is less than the square root, then the potential is bounded, cannot be confining. Moreover, if we have some excess condition that I did not describe, but let me say that there are some conditions that guarantee this, then we have that the potential is actually separated from zero, while if we add some Ascione condition, then we again get the x at -2 decay. So I want to stop here. Let me just say just one last thing, that is to say, what can we see here is that square root of eta is some sort of discriminant between possibly admitting a zero-energy eigenvalue and not admitting a zero-energy eigenvalue, and plays more or less the role of a critical mass. Because here, eta, in the relativistic case, is the mass. Is actually a quantity that depends on the mass. So what we're saying here is that if the eigenfunction takes into consideration something that is greater than a certain critical mass, then we cannot have zero as an eigenvalue. And well, I have a lot of things to say, but I stop here because I cannot. Well, okay, I think I can stop here. Yeah.
Okay, thank you very much for this so interesting talk. Are there any questions or comments? Enrico?
I thought I killed them all, but actually Enrico survived to this.
Yes, yes, I'm still here. Yes, thank you. No. I have a sort of a trivial question. So in a sense, you're assuming some properties of the eigenvalues, trying to reconstruct a potential eigenfunctions. Sorry, yes, not eigenvalues, eigenfunctions, so eigenvectors, and trying to reconstruct properties of a potential that could have that eigenfunction. So now, of course, the question comes, so once you have a potential with those characteristics, what else can you say about the system? This is my first question. And then I have a second question related to the approximation of the Dirac equation. So you were saying that these sort of Klein-Gordon-like operators are not fully relativistic. You mean in the sense that they do not describe a relativistic atom, or?
Yeah, they do not properly describe the relativistic atom.
Okay.
Due to so let me just answer to this question first, and then the other one.
And then you go to the other one, and then I stop here. Yes, thank you.
So this does not describe in properly the relativistic atom. This is due to the behavior with respect to the time derivative and the space derivative, because actually, well, in a certain sense, the presence of the non-locality in the equation, while the time derivative is local, causes a sort of asymmetry in the effect with respect to the actually time and space derivatives. So despite we have a Lorentz invariant, we lose track of the fact that space and time plays more or less the same role. And actually, it's a quite complicated thing, because one just sees the equation and says, okay, it seems to be quite relativistic and so on. But actually, that's the real motivation that Dirac used to say that this equation does not work, is that here we have a certain local behavior with respect to time. Here we have a local behavior with respect to space, but then we should have in relativity that in a certain sense, we say like this, time and space should be in a certain sense interchangeable. And he said also that it should be local. There should be some local interaction and not no local one. But then in some recent works, a lot of people actually prove that despite this not being the full description of a relativistic atom, it's quite near. It behaves like we are describing actually the relativistic atom, despite we lose some of the properties of the Dirac equation. And actually, that's because this equation here is much more similar to the Klein-Gordon wave equation that we could actually think, because to obtain the Klein-Gordon wave equation, we just take the square of the previous relation, then we map as before. So
yes, there is an anecdote that Schrödinger was originally deriving equations like these ones.
Yeah.
And then he saw that they were not working. I mean, the myth is that he went for a famous trip, etc., and then he was left alone, and he started working on this thing, and then he manipulated his symbols, got to this equation, and so it was not working. And then he tried with the classical dispersion relations, and he got out a paper somehow. Yes, but so in fact, it is in the notes of Schrödinger, if I remember correctly, that he derived something like that. There is another point, however, that about locality, but maybe I have to stop here. Sorry, and I leave you.
Yeah, that's quite an intriguing. It's actually an intriguing point, because actually describing a relativistic atom is not quite simple, and relativistic quantum mechanics is also quite discussed between the physics. I'm not a physicist. Let me just stress this. So I'm talking about things that I know from the tip of the iceberg. Okay, so as far as I could hear from physicists that work with me where I'm actually at, they say, well, let me just stress that relativistic quantum mechanics is not quite clear as it should seem, because there are different axioms that try to describe the same theory. And they all seem to work, but they are quite orthogonal between each other. For instance, the Klein-Gordon equation and the Dirac equation are not quite interchangeable. But then, so for the other question that is, that I forgot actually. Oh, yeah, right. The fact that after we deduce something like this, what can we say about the system? Well, that's quite the next point of the work. What can we say about the systems? There's one point I want to underline in this case, that is going back here, is that, for instance, do not admitting any zero energy eigenfunction, but admitting a zero energy resonance. And let me just stress that the previous result, for instance, this one, as soon as I get there, the power like one. So I can just stress out where it is. It's long. It's too long. Okay, for instance, this one holds for any value of kappa between 0 and d alpha. But I said before, function like this for kappa less than d4 are not in L2. So if I choose kappa small enough, I'm saying, well, I'm not searching for potential for which the Schrödinger operator admits zero energy eigenvalue. I'm searching for potentials for which the Schrödinger operator admits a zero energy resonance. And then I have to guarantee that it does not emit any zero energy eigenvalue. That's another point, and that's another problem. But then that's because actually we could do it if here this should be kappa, but here we don't have kappa, so we can just say, well, we found a potential that could in theory admit a zero energy resonance. Does it admit a zero energy eigenvalue? Eigenfunction, we hope not. And then once we do this, we have something that could, in theory, be related to the Efimov effect, for instance. And could, in theory, be related to this some sort of universal but quite strange behaviors in which many body systems have pairwise unstable states and then altogether are stable. That's, however, that's something that we would like to work on. We were thinking about working on, but that's something that will require some other work. By now, what can we say is that since we are prescribing some behavior, first of all, we know when an eigenfunction cannot be a zero energy eigenfunction for a potential that behaves in a different way from this kind of behaviors. And then we also obtain some no-go conditions in which we have that if we prescribe the eigenfunction to decay too fast, then we don't have zero energy eigenfunctions. Sorry, if we describe the eigenfunction to go too fast, then we cannot have the zero eigenvalue. And well, actually, if you start from the potential, then see, well, if I start from this potential, I suppose that there exists a zero energy eigenfunction, then this eigenfunction decays like this, then this eigenfunction does not exist, actually. And that's an absurd. And so on and so on and so on. So what can we say about the state of the system is another complicated question that we would like to answer. I'm talking about a more wider audience than me and myself, sorry. We would like to investigate further. I hope I've been...
Sorry.
No, I just want to say, I hope I've been as much exploratory as I can.
Okay. Okay. Any other questions? Okay, then let's thank the speaker again. And thank you very much for this interesting talk. Thank you.
Thank you all for being here and alive, actually. It was quite, I know it's here, just to say here in Italy, it's 7:15.
Yeah.
So it's, and
yeah, the timing is evening talks are a bit late for the...
Well, for me, it's not a problem. I think it's